captioning next to the camera. And what we're working on right now is going to be this. Oh, I thought we had. Okay, let me go back to demography then. On it, between the two classes, I sometimes get confused. Slide 4. Okay. So we were talking about survivorship curves. Okay. And what survivorship curves give us is a baseline. Okay. When you're monitoring populations. For example, if you have a population of elephants, which is a type 1 curve, suddenly showing a high mortality among the younger elephants, something abnormal is probably going on, possibly poaching. Okay. Or if there's a sudden curve normally, then a higher catch limit of the adult fish can be recommended. Okay. I would, but I would like you to um, take a look at this article on CBC. Or is it not presenting? So if you look at this article, this is a rockfish, okay? And it's an endangered species, but it's gone from a very endangered species oh, that's bizarre because it should be picking up everything. Yeah, I'm on the better of the two networks. At any rate, the fish is rare, but and slow growing. Okay. Uh, they're usually overfished as bycatch. Yeah, I'm on the internet. It's completely wireless, so I don't have a hard wire to my office. Here, let me see if I can run a cable. Okay, I've hardwired myself in. Is that better? There's my chat. Okay, we'll try that for a while. Okay, so this rockfish, as I said, very limited numbers. Then in 2016, there was a massive birthing event. Okay, so before there were a few places you could go to and not catch any of these endangered rock cod, right? There were hotspots. Now the entire BC coast is the hotspot. So that's a problem. Okay. Um, the big problem for fishermen is that there's a limit on how many of these fish you can catch. Once you catch that limit, that's it. You can't fish for anything, which is really limiting the fisherman's season. So what they have to do then is they have to figure out new management technique for these fish. That's the issue. So that's why these survivorship curves are so important, because it can give you a baseline of what the population is doing and then let you know if something's going on to change that. Okay. Now, another term that's important is this one here, fecundity. Okay. It's the potential for a species to produce offspring in a lifetime. Okay. So this is different from fertility. Okay. It's the potential. Okay. So fecundity will vary with the population. The number of offspring also varies per species. Also, the age of sexual maturity varies per species. What's How long does it take a cat to reach sexual maturity? When can a cat start to reproduce? How long after it's born? Yeah, it's a few months. But for humans, How long does it take before a human can reproduce? Roughly. Yeah. Okay. Now what people get confused about is the difference between fecundity and fertility. So fecundity is the potential of a species to produce offspring in a lifetime. What's fertility? What do you think the difference is between the two terms? Yeah, Grant's got it, right? So if you're an only child, your mother's fertility was 1. If you're one of 13 kids, then your mother's fertility was 13. Okay? So fecundity and fertility are not the same thing, even though in general common English, they're treated as if they mean the same thing. Okay? The other thing that's interesting about fecundity in terms of the number of offspring is that the number of offspring is going to vary inversely to parental care. Okay, what does that mean? That basically means the more parental care you have, the fewer offspring you're going to have. So in Canada, what's the typical number of offspring that a family would have? Roughly, yeah, somewhere around 2 or near 2, nearly 2. Okay. Um, but think of something that's a lot more shorter lived. What's the number? What's the uh, fecundity of spiders? How many offspring could a spider potentially produce? And how long does a spider? Yeah, and how long does a spider live? Yeah, roughly spring to fall, right? About 2 seasons. They'll be born in April-ish, like right around now, and they die around September, October. Is there any parental care? No. Because of that, right, their number of offspring goes way up. So there's a trade-off. Okay. If you have parental care, then the parents put more energy into of their energy into the survival of the offspring, um, and therefore they don't have lots and lots of kids. On the other hand, if there's very little parental care, then the parents put all of their energy into producing the offspring, not into caring for them. So there's a trade-off between the two. How is she going to get it to you, Kirsten? It's not going to survive the mail. Okay, so when we talk about measuring population change, populations change because of these 4 things. Okay, birth, death, immigration, and emigration. And that's the last slide for this one. Okay, now, now we'll go into modeling populations. Okay, so this is a slide we just left on in the other slide deck. So these are the 4 things that are going to affect how a population basically changes. And that's basically it. That's the only thing. These are the four things that ultimately determine the size of any population. There are other factors involved, right? But those other factors influence these four. Okay. Now, delta pop, what's a triangle stand for? What does that mean? Change in. Okay. So the change in population size is equal to the birth rate plus the immigration rate or immigration minus death plus immigration, all divided by the initial population size. Okay. So that's the equation to calculate the change in population size. You're going to end up with a decimal number. Okay. Not a, I don't want to see a fraction. I want to see an actual decimal number. And I don't want to see a percentage because a percentage means something else. Okay. Now, there are two kinds of changes in population that you can have. They're defined as, sorry, I forgot that one. A closed population and an open population. In a closed population, the change in population size is only determined by birth and death. Closed populations have no immigration and no emigration. Okay. So, what's an example of a closed population? What kinds of populations have no immigration or emigration? No, they still have movement. They are isolated, but you still have people leaving. Okay, better example, population of Earth. Aquarium's a good example. Population, as long as you're not adding fish, right? But think of the population, human population on Earth, right? Do humans leave to go to other planets yet and live on other planets? Do we emigrate away from the Earth? From the Earth. I don't know of any permanent emigration from the Earth. No. And there is no one immigrating to Earth from another planet, right? So the human population on Earth is a closed population. Okay. Well, I think that's a pretty solid assumption. Okay. In an open population, all four of these apply. So the population of Canada is open because we are primarily dependent on immigration. There's some immigration that goes on too, but country populations are usually considered open. Okay, so that's the difference between the two. Okay, so in April, this is an example, population of frogs in a ravine had 42 frogs, increased by 263 tadpoles. Yes? Okay, bye-bye. Pesticide runoff killed 26 tadpoles. Predators consumed 8 frogs. In July, construction workers began clearing the ravine and ran over 12 frogs. Calculate the population growth rate of the frogs in the ravine from April to August. Okay. So it will be 263 minus 26 minus 8 minus 12. So minus 26 minus 8 minus 12 is 217. Then you take 217 and divide it by 42. And yeah, you're going to get around 5.17-ish. Okay. So all you're doing is plugging these numbers into this equation. So B was 263, D is 26 plus 8 minus plus 12. Okay, there's no immigration, there's no emigration. Divide that by the initial population size, 42. Okay, different from delta pop is the population growth rate. And the population growth rate is the fractional rate at which the number of individuals in a population increases or decreases. So it's a change in population over a unit time period, expressed as a percentage. So population growth rate is a percentage. Delta pop is a fraction or a decimal. Okay? So you have to multiply it by 100. That's really the only difference between these two equations. Yeah. Okay. Now, what's exponential growth? How many of you, first off, before that, how many of you have taken calculus? 1, 2. Okay. What we're going to talk about when we start talking about exponential growth, I'm going to be talking about it using some of the terms from calculus. However, you don't need to take calculus or have taken calculus to understand what's going on. I'm going to do this algebraically. Yeah, correct, Kirsten. Right? So the first population growth model that we're going to look at then is what we call an exponential growth model. Okay. This is for species that reproduce continuously and therefore have the potential to increase exponentially. Okay. Bacteria, humans are another good example, right? If you look at the growth of the human population, it's very much exponential growth. Okay. So as an example, if you take bacteria, which can reproduce about every 20 minutes, and you start a population with one single bacteria, the population will double every generation, right? 1, 2, 4, 8. After 8 hours, which is 24 generations, the population will be over 16 million. Okay. After a single day, that's 72 generations, the population will be nearly 5 times 10 to the 21st cells of bacteria. Is that realistic? No. Okay. So this is what a growth curve like that looks like. Okay. So it's described as a J-shaped curve. What you should notice is that the x-axis, the generational time, remains constant. But what happens to the y-axis? What happens to the number of individuals each generation? Well, it goes up, right? So you start off slowly. If you think about this, this is rise over run. So this is the slope, really. So the slope in generation 1 is pretty low. But look at the slope in generation 5. Actually, generation 4 is easier to see. It's going from here to here in one generation between those 2 points, much steeper, right? So basically, the slope of the line gets steeper and steeper and steeper, slowly approaching the vertical. And that's exponential growth. So all populations have the potential for exponential growth. I'm going to open the door again. It's a little warm in here. And in a given time period, if we ignore immigration and emigration, then the change in the population size is going to equal the number of births minus the number of deaths. Now, in math, we use the symbol d, lowercase, to indicate an incremental change, a very, very small change. So what I'm basically saying is, you see here, the distance between one generation to the next remains constant. What if I made the generation time smaller? What if instead of measuring the time between one generation and the next, I measured the time between half a generation or a quarter generation? Okay. What am I taking if I make the time difference so small that it's actually a point? What am I actually measuring then? That's what a derivative is. Yeah, instantaneous slope or the tangent. Okay. So what I'm basically measuring is the tangent of this line. Okay. When I do that, that's when I'm taking the symbol d instead of the delta sign. Okay. So a very infinitesimally small time frame. Okay. N is the population size. So dn, and this is one variable. It's not d times n. It's the variable dn. Is the change in population size. dt is a change in time. So it's a very incrementally small change in time divided by a very small, which is so you're taking a very small incremental change in number divided by a very small incremental change in time. Okay. Now we know capital B is the number of birth. Capital D is the number of death. Okay. During that time period. So if we take dn and divide it by dt, then that term has to be the change in population size over that infinitesimally small time. Okay. So we can say, since we know B is the number of birth and D is the number of death, we can say that B minus D has to equal dn divided by dt. Okay. And we can use this equation for any population if we know the exact number of birth and death. The problem is, for any population, we probably don't know what capital B and capital D are. Okay. But what we can do is we can calculate the difference between these two numbers. Okay. Now, the difference between birth and death is the per capita growth rate. That's represented by the lowercase r. Okay. The per capita growth rate has to equal the per capita birth rate. Okay. And the per capita birth rate is the number of births in a population in a given time, okay, divided by the population size. Okay. Similarly, we can calculate a per capita death rate, number of individuals that died in a population size, in a population divided by the size of that population. So capital D over N. Okay. So if you have a population of 2,000 mice and 1,000 mice are born and 200 mice die every month. The per capita birth rate is 0.5 individuals. B is equal to 1,000 over 2,000, which is 0.5 births per individual per month. And the death rate is 0.1 individuals. 200 divided by 2,000 is 0.1 death per individual per month. Now, what does that mean? How do you give birth to half an individual in a month, or how do you die 1/10 of a death, 1/10 of a death in a month? Okay, do we actually do that? How do you die 1/10 of a person? So what do these two numbers actually represent? When we say that the birth rate is 0.5 births per individual per month, what does that actually mean? Average over a population, right? So in reality, no mouse can give birth to half an offspring or die 1/10 of a death, okay? What these rates give us are the birth and death rates averaged over all the mice in the population, okay? So whenever we talk about per capita rates, you have to refer to it over a specific time period. If it's an organism that lives a long time, like humans, the time period will be in years. For organisms that have very short lifespans, like say fruit flies, we'll talk about it in terms of days. Okay. Per capita birth and death rates can be calculated from data in the life table if you're starting from scratch. Most times I'll just give you the problem. Okay. So we can now revise the population growth equation. We know that dn over dt, the population growth rate, is equal to the birth rate minus the death rate. But we said back here, right, lowercase b is equal to capital B divided by n. So if we solve for capital B is equal to lowercase b times n, right? So b can be substituted by lowercase b n, and d, capital D can be substituted by lowercase d times n. We can factor out the n, so now we get the per capita birth minus per capita death, right, rates multiplied by n. Now, the difference between the per capita birth rate and the per capita death rate is the per capita growth rate, r. So we can rewrite this equation as dn over dt is equal to r times n. This is the equation for exponential growth. Okay? If you're confused, I'm going to go through an example and you'll kind of see what I mean. This is also in your textbook. So let's see, my Nelson. We go to Unit 5. Chapter 12.3. What I'm doing right now is I'm going through pages 600 and 601. That's where I am right now. Then on 602 is the rest of this that I'm about to talk about. Okay? Now, so if B is greater than D, R has to be positive. Population is growing. If B is less than D, then R is negative and population is shrinking. If B equals D, then R is equal to 0. Population is not growing. That's something that we call ZPG, or zero population growth. Birth and death still occur, but the number of births is about equal to the number of deaths. That's what that means. By the way, I forgot to mention this earlier. I've got a meeting at 2 o'clock, so I will be ending this class a little bit early today, okay? All right, so here's an example. Let's say for that population of mice I was talking about earlier, right? With an initial population of 2,000. We said that the per capita birth rate was 0.5, and the per capita death rate was 0.1. That means R has to be 0.5 minus 0.1. So R is 0.4 mice per individual per month. Okay. So in the first month, the population is going to grow by 0.4 times 2,000, which is 800 mice. In the next month, starting with a population of 2,800, R is 0.4. Population will grow by 1,120 mice. I'll be right back. Yeah, I'm fine. The population grows every month, even though R is constant. So it's going to produce a J-shaped curve. So if you look at the next slide, and this is also, that is from your textbook, page 602. From right here. Okay. So you can see what happens to the population size. Every time I'm taking this population and multiplying it by 0.4. That gives me the net monthly increase. And you can see how the population grows over time. In just over a year and a half, so by month 19, you'd have a population of over 1 million mice. Okay? So this is what we mean by exponential growth. Now, try this example. That's, yes, okay. I got to go through a few more things first. Okay. Think of another population with unlimited resources, no predators, no parasites, no disease. Okay. Under these conditions, which are really unrealistic, right? I don't know of any natural population with unlimited resources, no predators, parasites, or disease. But if that happened, the per capita growth rate is going to be, birth rate is going to be really, really high, and the per capita death rate is going to be really, really low. So the per capita growth rate is going to be as high as it can possibly be. Okay. This maximum per capita growth rate is called Rmax. That's the rate at which the population would naturally grow if there were unlimited resources, no predators, parasites, or disease. Okay. So the intrinsic growth rate, or Rmax, is the rate of population will grow under ideal conditions. Okay. Generally speaking, Rmax will vary inversely with generation time. What does that mean? Okay, these are the Rmax values on the y-axis. This is how long it takes for how long a generation lasts on the x-axis. Okay. Note, for organisms with really, really short generational times, their Rmax is really, really high, right? Bacteria, paramecium, malarial parasite, their Rmax value is really, really high. But look at our organisms that have long generation times, right? In that case, our Rmax is really, really low, which kind of makes sense if you think about it, because what's the parental care of a bacteria like compared to the parental care by a sheep or a human? Yeah, none here, quite a bit over here. So these organisms are putting their energy in towards making sure the offspring survive. These guys are putting in their energy to produce lots and lots of offspring. Because they're producing lots of offspring, their Rmax value is high. We don't produce that many offspring, therefore our R value is really low. Okay. Okay. Something that's useful when we're comparing populations is something called doubling time. Okay. Doubling time is the amount of time it takes for a population to double in size. A good way of approximating it is with this equation. Doubling time is equal to 0.69 divided by R, where T sub D is doubling time and R is your per capita growth rate. So if a population has a growth rate of 4%, 0.04 a year, then the time to double that population is going to be 0.69 divided by 0.04, which is 17.25 years. Okay. That's actually a pretty easy equation to calculate. So try the three sample problems. Well, let's go through the example. So we have a single cell marine algae, estimated 125,000 cells. So N is equal to, or it should be a capital N. There's my N. My growth rate R is equal to 0.16 a day. So what is dN divided by dt? How do you calculate that? They've given you R, they've given you N. Right, so just do R times N. So plug that into a calculator, tell me what you get. Right. Well, you do the math. So the instantaneous growth rate, the initial instantaneous growth rate was 20,000 individuals. Okay. So that's how much the population grew by. Okay. The time to double the population is always going to be 0.69 divided by R. Since R is 0.16, it's going to be 0.69 divided by 0.16. That should give you 4.3 days to double the population. Okay. What's the size of the population after 5 doubling periods? Okay. Well, it's going to be 125,000 times 5 doubling periods to the fifth, which should equal, I think it's something like 4 million. 125,000 times 2 to the power of 5 Yeah. So after 5 doublings, the population is going to be 4 million individuals. Okay. Does anyone not see how I did these three calculations? If so, if you want me to go over it one more time, raise your hand. Okay, look. Yeah. Okay, so that's all that is. All right, it's 1:18. Take a 10-minute break. We'll get back together at 1:30. And we'll have about a half hour left. I don't go into too much detail of that. That's really for a more calculus-based class. So probably next year, if you have ecology, they'll talk about it then. And they'll talk about much more complex models than this. Okay. Now, the limitation of exponential growth is that real populations do have limited resources, predation, parasitism, and disease. Therefore, a birth rate that drops and a death rate that goes up. Also, a lot of populations don't breed continuously. Many have breeding periods. So think of things like deer or fish. So the population size needs to be compared year to year rather than at any 2 points in a year, right? Because the increases only happen in a certain time period. Okay, so the other population growth model that we're talking about is in a limited environment. So in a limited environment, resources are limited. And so there's something called a carrying capacity, the maximum population size that a habitat can sustain over a long period of time because resources are limited, right? If you only have a certain amount of food, there's only a certain population size that you can sustain. If the population size goes over the capacity of the ecosystem to feed that number, the population has to decline, right? Because individuals are going to starve. And vice versa. If the population size is lower than what the resource can sustain, the population size will go up. Okay? Carrying capacity is not a fixed number because the resource amount can change, right? If it's a really good, let's say for a population of rabbits, you get a nice, warm, good summer. So you get a lot of grass growing, okay? Well, that can support more rabbits, and so carrying capacity goes up. But in a year where there's a high drought, the grass doesn't grow as well, less food available, so the population size has to drop because there's less food to eat. Okay, so carrying capacity will vary depending on the availability of the resource that you're looking at. Okay, so the growth curve in a limited environment, yeah, exactly, is what follows what we call an S-shaped curve. Now, again, this is a model, it's not reality. So the graph starts out slowly, then initially goes into an exponential growth phase, but then as the resource becomes limiting, the population growth slows down and then eventually levels out. Now, obviously, no real population shows a smooth curve like this. They're going to show dips and swings as the population actually over and undershoots the resources available. But if you average it, you're going to get a nice looking curve like this. Okay, so in the logistic growth model, okay, dn over dt is equal to R max, the intrinsic growth rate, times n, the population size, multiplied by this term, k minus n over k, where k is the carrying capacity. Okay, so let's see what this term does. Okay, so if we compare the exponential growth model to the logistic growth model, okay, what's the effect of this term? What's the effect of k minus n over k on dn over dt as k gets close to n? Or as n approaches k is what it should say. As the population size approaches carrying capacity. Right? As n approaches k, then k minus n over k goes to 0, approaches 0. So dn dt, the growth rate, has to slow. Right? So the blue line is exponential growth. The black line is a carrying capacity of 1500. So under logistic growth, as n gets to 1500, you're eventually going to get to 1500 minus 1500 over 1500, which is 0, times n, which is 0, times 1, which is 0, gives you a growth rate of 0. Okay? And that's why the curve flattens out, whereas the exponential growth, which doesn't have this term, continues to go up. I suppose. Okay, now, so you've got a population of spotted butterflies showing logistic growth. Okay, the carrying capacity of the environment is 500 butterflies, and its intrinsic growth rate, R max, is 0.1. Determine the population growth rates based on population sizes of 50, 100, 200, 350, 480, 500, and 525 butterflies. Okay, I think this is in the textbook. Yeah. So if you look here, okay, so the solution is on page 607, yeah, of your textbook. Okay. So K is 500, R is 0.1. The formula is this. So given the information, there's R max, there's the N values. So when you plug this in, these are the growth rates that you're going to get. Okay. So if you want to look at page 607, that'll give you the solutions for A. And then B, describe the relationship between population size and growth rate. As the population increases, the growth rate increases as well. As the population approaches carrying capacity, the growth rate levels off. Note that there is negative growth if the population size exceeds the carrying capacity. So that's on 607, 608. So take a look in the textbook on page 607, 608 to see how this problem is basically solved. I'll leave it up to you if you want to copy this into your notes or not. Do you want to copy it out or do you want to just look in the textbook? If you want to copy it out, I'll leave it up and give you 5 minutes to copy it. Otherwise, I'll move on. Which do you want me to do? Move on? Okay, let's move on. Okay. Anyone know what this is a picture of? What the two animals are? Okay, it is a Canadian lynx. And what kind of bunny is that? Yeah, snowshoe hare. Okay, so if we look at changes in carrying capacity, okay, so that smooth logistic curve that I showed you, right, as I said, isn't reality. Populations actually cycle. They're going to weave up and down, okay, due to things like predator-prey interactions. Okay, so the black line is the number of snowshoe hare. Okay, that's this axis over here. The red line is the population of the lynx. Okay, in thousands. So the rabbits go from 0 to 160,000, and the lynx go from 0 to 9,000. Okay. So what's the population? Where's the carrying capacity? If you had to draw a line, where is the carrying capacity for the lynx, and where is the carrying capacity for the snowshoe hare? So let's start with the snowshoe hare. Where would you put the carrying capacity for the snowshoe hare? What value of rabbits? Okay, so Grad says around 80,000. Okay. What would you put the carrying capacity of the lynx? Remember, the lynx is on this side. So around 6. Okay. So Grad's looking at the peaks, basically, is from what I can tell. Okay. So the carrying capacity of the hare population is going to be about just over 40,000, not up at 80, right? Because what you want to see is the population over and undershooting the carrying capacity. And the population of lynx, its carrying capacity is about 3,000. Okay. Now, here's another question. How do we get this data? Look at the years that this data is for. How did we get the data? We didn't have, yeah, Okay, which company is this data from? Yeah, this is the Hudson's Bay Company, right? This is the fur trade. These are the pelts of lynx and hare that were brought in during the fur trade. Uh, and these are the thousands of animals that were basically caught. Okay, so we have pretty good data for the population of lynx and snowshoe hare from the early 1800s to the early 1900s. Okay, so this is all data generated in Canada by the fur trade. Okay, so historically, we've had good data on this kind of stuff. Okay, so population growth models and life histories. Okay, what's the best life history for any organism? Well, if you have sexual maturity occurring at a young age, a very long lifespan, very large number of offspring, and high parental care, you're going to get a really high Rmax value. But this isn't realistic. Why not? Not only that, how much energy would the parents have to have this work? Ton of energy. And energy uh, is probably the most limited resource that we're talking about when we're talking about uh, growing an organism. Okay? Because resources are limited. Okay? The environments are not stable. Okay? So for those two reasons, no real organism follows that strategy. Okay? So what we actually have are what we describe as R and K selected reproductive strategies. Okay? So R selected organisms are organisms that live close to the biotic potential. So if we go back to the logistic growth model, okay, an R selected animal is one that lives right here, right? What would you expect in terms of characteristics for an R selected animal? Would you expect them to have long or short lifespans? Shortish. Yeah. If you're living close to the biotic potential, you're reproducing as many offspring as fast as you quickly can. Lots of offspring, very short lifespans, very little parental care. That's R selected. Early reproduction, so early sexual maturity, many, many offspring, very little parental care. Insects, lots of plants show R selected reproductive strategies. If you're K selected, you live close to the carrying capacity, right? You're at the top of the curve. Late reproduction, very few offspring, invest a lot in raising the offspring, so lots of parental care. What would humans be? R selected or K selected? Yeah, we're K selected. Primates and coconuts. Okay, this is due to trade-offs, right? This is R selected organisms, K selected organisms. Okay, so there are trade-offs between the number and size of offspring versus survival of the offspring or parent. Okay, so most weedy plants like dandelions grow quickly, produce a large number of seeds, ensuring that at least some will grow into plants and eventually produce seeds themselves. So this is an R-selected species. Is an R-selected species then survivorship curve 1, 2, or 3? Okay. So if we go back to where's the slide? Yeah, so it's type 3, right? This slide here. Right? It's a type 3 curve. Dandelions will be here. On the other hand, if you look at the coconut, right? Few offspring, but very large seeds, lots of parental care, type 1. Okay? As the Far Side comic here says, of course, long before you mature, most of you will be eaten. Okay? So you can use these reproductive strategies to basically predict how an organism is going to do in its environment. Yeah, this is the last slide. So how successful are these seals going to be in their environment in terms of survivability? Well, they should be fairly successful. Seals have a lot of parental care, right? They're usually protected, and only a few of them will be eaten by predators. All right, that's the end of this lecture. I'm going to stop it right there for now because I have to go to this coaches meeting next. So you're basically dismissed. We're going to start looking at the factors that affect population size in tomorrow's lecture. I'll also probably give you the assignment for this unit tomorrow. All right? It's a pretty straightforward one. So that's it. Remember to get those photosynthesis gizmos, not photosynthesis, protein synthesis gizmos in if you haven't completed it yet. Otherwise, you are dismissed.